This is negative because now you may think, why is this fx going to negative side? Why is this one negative and this graph is going to negative? Why is this? Because fx, when we take work, here we take work as half times base times height, so base as xf. Okay, no problem in that, but height we are taking it negative. Why we are taking negative? If we return back, we take the formula for fx is equal to minus kx. Okay, so minus kx is representing the downward. So if you look, it takes minus kxf, so we'll take this minus kxf. So this will be w is equal to, if you multiply this one, it will give us what? Minus half kx square. So let's go. Now let's think if you have a starting point like an initial extending and you have a final extending. If you want to find work here, you will use a formula which is this one, the last formula in this slide, in slide 8. So which is, if you want to find the work, what you have to do is you have to subtract the final extension, which is x final square, minus from the initial kx square. Then the final formula will be minus half k, this is a spring constant, xf square, this is the final extended length, minus, which is the minus will be here, plus. Okay, so we will delete this one, this will be half kx square I. Okay, now let's go to elastic potential energy. The work done by ideal spring depends on the initial and final position of the movable end. So like we said, the initial and the final of the movable end, but not on the path that was taken. So we don't care about the path here. Therefore, the force exerted by ideal spring is conservative. We can associate a potential energy with it. So if it is conservative, it doesn't mean there is no waste. Okay, so we can associate potential energy with it. The kind of potential energy stored in spring is called elastic potential energy. So for potential energy, you may hear potential energy. So you may hear in your level, sorry, this one, let me do energy. So potential energy, you may heard two things about potential energy. One is this one, elastic potential energy. The another one is gravitational elastic gravitational potential energy, not elastic, gravitational potential energy. Okay, so this formula is mgh, and it is stored energy that depends on the mass and the height of the object. Okay, and elastic energy, potential energy, is a little bit different from that. It depends on the spring constant and the extension. Okay, so we're gonna discuss about this more. Okay, for this we will discuss later or some other videos. Okay, just as for the gravity, the change in elastic potential energy is negative for the work done by the spring, so it is negative. Okay, they are opposite. So we have change of elastic potential energy, which is elastic, is equal to minus work of the spring. Okay, so we know the formula of spring, right? So which is this one, work is equal to minus half k x final square plus half kx initial square, right? But when, because there is minus, now we have to multiply it by minus. The formula for potential energy or elastic potential energy is going to be positive half kx final square minus half kx initial square. Okay, now elastic potential energy stored in ideal spring. So elastic potential energy. So potential energy is mostly with stored energy. So if you want to find like for stored ideal springs, you can use the formula U elastic, which means elastic potential energy is equal to half k x square. So if x is 0, which means the spring is relaxed, that means we don't have elastic potential energy. Okay, so if we don't have x, which means the spring is relaxed, then we don't have elastic potential energy. Understand? Now let's go to elastic potential energy and some conservation of energy. Okay, conservation of energy with more than one form of potential energy. When applying conservation of energy using, we have a formula here, NC is equal to delta K plus delta U. This is kinetic energy, by the way. Kinetic energy is equal to potential energy. Always when you talk about conservation of energy, the summation of this one never change. Okay, maybe this will increase or decrease, and simultaneously this one increase if this one decrease, and if this one decrease and this one will increase. Like if a ball is falling from a building, it is losing its potential energy because it is losing height, but it will increase its speed and it will increase its kinetic energy. So it is change like change of energy. There will be no waste of energy. For now, with two forms of potential energy, so we have two forms, I already told you. So we have change of U is equal to change of U, which means U means potential energy. So potential energy, so if we add gravity here, or gravitational, so gravitational potential energy, I already told you, plus change of U, elastic. So we have to think, we have elastic potential energy and gravitational potential energy. WNT is the work done by all forces other than those included in potential energy. When WNC is equal to 0, the mechanical energy K plus U is constant. So if work done, or the total work done by other than those included in potential energy are 0, we have K plus U is constant. So we use this ideology in many problems to solve some equations. So let's see this one, how can we solve it? In many hardware stores, bulk nuts and bolts are sold by weight. A spring scale in stores stretches 4.8 cm when 24 Newton of bolts are weighted. On the scale, what is the distance in centimeter between the calibration marks that are marked in increment of 1 Newton, assuming an ideal spring?